on the regulatory, specifically on the regulatory and the load management issues, energy management issues relevant to the renewable and storage integrated the future distribution network. And this team is working on this particular theme. Before I think I would like to invite all the speakers of this session, Dr. Anurag, Ankush Sharma, and Sanjeev. But before that, I would like to introduce the US team who have kindly agreed to visit us. And they are here since 3 days. So we have Professor Anjan Bose from Washington State University, Dr. Anurag Srivastava, who has recently moved to West Virginia University, Sanjeev Panala, they are the technical co-leads. Niall Sulz could not come, but they are here from Washington State University. And then we have Gary from Bunsen McDonnell, and we have Rob from NREL, and Murli Baggu from NREL, and Professor Chanan Singh, I think, was there. So he may be, yeah. So you are here, sorry. So, and Professor Venkata, actually, I mean, they are very senior. One very great thing I feel proud that if you see how many IEEE fellows are there in this team, I think almost 80% people are IEEE fellows. And then INA fellow, even foreign fellows, we have Professor Bose and Professor Chanan Singh here. And this year in section 5 of Indian National Academy of Engineering, 2 people were selected from electrical engineering category I'm talking for Indian National Academy Fellowship. And I'm happy to say that both are the team member of UI Assist, Professor Santanu Misra and Samantre. So they recently got this fellowship, but we have a large number also in there. So a very eminent team. So this particular one, I think I request all the speakers to come on the dais. And there is a challenge. Four professors talking in 1 hour about a topic is really a challenge. So I'll be very quick. I'll just give a very brief background, and then Anurag will briefly tell about the project, and then followed by Ankush Sharma and Sanjeev Panala. So, friends, I mean, this is very well known to all of you that the power sector is very fast getting reformed and transformed because of various reasons, actually. One is because of the climate change, which we are experiencing, and because of the global weather and seasonal variations we are experiencing, mainly because of greenhouse gas emission. The whole world is aware of that, and they are working together. And I think there are few data they bring out. IPCC brought out projection that by 2050, the global temperature will rise by 1.5 degree. Everybody is scared what will happen to the community. So a lot of damage will be there if it is not overcome. So that is one. And then many new technologies like power electronics devices, the converters are getting fast developed thanks to the material science technology development and also ICT technology, which is being deployed in the distribution and the transmission network to make it more intelligent and provide better control to the system. So smart grid, wide area monitoring system, DMS, ADMS are coming up. To add to the complication, the electricity market actually is also getting reformed at various stages. It have been implemented and getting implemented also. So the whole changes are happening. So, and transport sector, I think we are going for more electrical vehicle. Now, this is the projection by World Energy Transition Outlook that if you have to overcome this 1.5 degree Celsius temperature rise by 2050, how much carbon emission you have to reduce from different sector. So if you see here, the power and heating sector contribution is maximum, expectation is maximum. 13 gigaton of carbon oxide emission you have to reduce, followed by the industry and the transport sector. Now, when you work on these two sectors, power and transport, again, we are emerging to electrical system only because electrical vehicle will come, and so the changes in electrical system will be coming. And then many other reports have come. This is ARENA report in 2021, that how the generation pattern have to be revised by 2050. So a lot of the renewable energy have to be picked. That is very well known, actually. So carbon emission have to be minimized or eliminated. So the conventional power plant share will be less, very negligible, and renewable power share will be there. So that is the projection. I don't know how much we can achieve. But India also has a very ambitious program. This is our scenario as of October 22. I think CA publishes very regularly the report, and also the MNRE for renewables. I think there is some line have been shifted here. So if you see the share of renewable in terms of installed capacity is about 29%, 30%. But energy, in terms of energy, it is less. But coal is still dominant. That I think we had long deliberation in our NPSC also, that we cannot do away with coal. We have to remain with our power plant with coal generation will remain, but we have to go for cleaner technology of coal. So we have also a very ambitious plan of adding 450 gigawatt RES by 2030. So I don't know how much we will achieve, but I think the whole government and machineries are working on that. Now, distribution sector, which was earlier very much neglected, I think it was politically reasons it was being expanded, no planning was there. Now, I think a lot of attention have been put on the distribution sector, because the generation will now shift to the distribution side. Distributed generators or small generators will be there. So large deployment of renewables will come, mostly PV and wind in our Indian case. And then we have to make it smart. So advanced metering, ICT infrastructure have to be put. And to take care of variability of RES, we have to go for some kind of storage. I think many people have talked about that. EV charging infrastructure is getting enhanced. Government fortunately has several programs starting from APDRP and then revised one version and IPDS now, which is actually performance-based scheme. And then many other schemes for electrification and also village electrification specifically, are to take care of the financial problem of the DISCOMs like Ujjwal DISCOM, Assurance Yojana, and so on. So they are also supporting several schemes. But the distribution network, which was earlier passive, has become now active, will be becoming an active network. Now we talk about renewable, but they pose several challenges. One is the variable nature of the generation. Solar, daytime it is there, at night time it is not there. Throughout the day it is varying. If cloud is there, then you have real facing problem. Similarly, wind. So to manage that, you need accurate forecasting and power balancing. Every second, I think minute to minute, you have to balance. Voltage and frequency control will become more challenging. Then stability problem will become more pronounced because of the loss of inertia when you add sources like PV. But fortunately, these power electronics components and intelligent or the converters we are putting, smart converters, they are some capability to support reactive power with the loss of real power can be exploited. So quality issues will be there. There is a need for advanced distribution management system. Microgrid will come up, their management, and protection also becomes challenging because the flow will be bidirectional. This is a very picture I think I have used several times, but I think this was created by Ankush Sharma. So this conventional way, the unidirectional power flow was there. ICT infrastructure was less in the distribution at least. But now with the penetration of renewables, I think the direction of the power flow will become the two-way, and to monitor and control them, you need strong ICT infrastructure. So that is basically the transformation to the smart grid. Okay, and then grid is going to be seamless, starting from big generator to the consumer end. So future grid will be a seamless grid. Now, active distribution network, I think this is a very representative diagram. Some picture have been taken. So this will have ICT and a cyber infrastructure layer laid over the power layer, and many controlling devices will be installed to take care of the generation which are being added at the distribution end, and their local management, and the larger side, I think the distribution side management will be there. So, and protection also will become some kind of adaptive or setting protection. So I'll just tell you that the distribution, when you talk, there will be 3 levels of controls. Because most of the renewables will be integrated through power electronic converters. So primary control, where you are controlling the voltage and current, or maximum power you are extracting, and then you are operating them together. So for that, group control may be utilized. And then secondary control, if you are forming a microgrid and several sources and the storage is there, for their optimal balancing and voltage control and stability control, islanding detection, if it is grid connected, management. So secondary control, which is also a microgrid energy management system, will be there. And tertiary level, which is at the distribution network side, we have the distribution management system, or advanced version, which also takes care of the renewable management and also the demand side management will be embedded with proper forecasting and control tools. And then protection also challenge has to be addressed. So this is the background of the changes which are happening in the distribution network. With this background, this project was taken to address almost every aspect, including the cyber security aspect associated with the large ICT infrastructure we are going to create. So I will invite Anurag to tell, but these are the consortia members. I think we have 15 from India side and 16 from US side as on today. It is mix of academic institutions, national labs, utilities, and industries. And one local NGO is also involved, Shramik Bharti, if you see on our side, specifically for our village deployment. And these are the current leads of the work. So I request Anurag to tell more about this project very briefly, and then we'll go to some other details. Thank you.
All right, thank you. So as we provided the background on the project, the objective is basically to enable the distribution grid to exactly solve those challenges which was discussed. So make it carbon free and utilize DER in optimal way and manage those to meet our objectives. It also has a specific focus on developing and demonstrating the DSO function, and with the microgrid and distribution system and ICT all considered in this whole objective. So you see the layer diagram, which start from device level, which is the DR control, and then all the different services that DR can provide, going to the microgrid level and secondary and tertiary control, and then outer layer where the distribution system grid operator, if they have visibility into DR to do through DMS. So we do have a different theme area, 11 themes, and each theme was organized for internal purpose so that we can manage the team in providing the expertise for each of these different challenges. So theme 1 is all about project management. Theme 2 is more about benchmark system development. Theme 3 was about energy storage analysis, and theme 4 was macrogrid active distribution systems. Theme 5 about cybersecurity and also cyber resiliency. Theme 6 is DSO function, all in terms of EMS. And 7 was market and regulatory aspect. And then we had a theme 8, which is about testing and validation with multiple test bed in real time, in offline, and also lab scale. Then theme 9 is about using those and implementing. And then theme 10 is about more impact on all the different aspects. And finally, theme 11 is about workforce development. So we do have a lot of field demonstration. We'll talk about that later too for both sides. A little bit more detail on each theme. So theme 3 has several different tasks it's like an objective and has several different tasks, starting from sizing and sighting, modeling, storage, charging, discharging, and control, development, health monitoring, life extension of storage. We also have a task where we look at with more and more storage, what happens to transformer life, and then other analysis that is needed for integration into the grid. Theme 4 in microgrid, we focused on converters for integration of sources, controller design at different level, and also protection. Then theme 5 was looking at the landscape of cyber systems and how to detect, how to mitigate, how to defend against cyber attacks. So of course that requires a lot of simulation. So all the tasks relates to different aspects, including IoT and different layer of cyber system into the distribution grid, including microgrid too. Then we had theme 6, which is very broad and looking at more number of aspects, because it is all about what we can do in the control room and how we can support through engineering analysis, right? So starting from sensing and data analytics to using that data and making sense out of it, of course, with solar and PV and all connected, monitoring those, then load profiling and forecasting. System reconfiguration is part of that, state estimation, and then optimal operation of DER for different possible services, volt war control and demand side management with demand response, and then reliability assessment with DER, and then finally how it will interact with TSO. And then comes the theme 7, which is market and regulation, regulatory aspect, with, addressing those issues, what kind of different market architecture we can have, and then how do we integrate those market mechanisms into different services, starting from voltage control, and then validation was embedded in each of these. So here also, and then finally with lab scale demonstration for this. Then theme 8 is all about different kind of test bed in offline, in different time scales too. And we do have several different test bed, in US and India. Okay, well, at this point, I will invite Ankush to talk further about the project in India.
Thank you, Dr. Anurag. So, as part of our theme 8, we have 8 lab pilots. One is at IIT Kanpur, which talks about the reconfigurable test bed. And then in IIT Bhubaneswar, the objective of this test bed is the protection aspect to verify. IIT Roorkee has AC/DC microgrid test bed. And IIT Delhi, DER integration into the microgrid. Then TERI has the test bed, which talks about the operational and control aspects of microgrids and battery energy storage system testing. IIT Madras, storage integration in microgrid is the theme of that test bed. Now, as part of theme 9, we have field pilots to be implemented. Here we have 5 field pilots in India and 5 in US. In India, we have a rural pilot near IIT Kanpur, which we are executing with the help of Dakshinanchal Vidyut Vitran Nigam and Shamit Bharti Foundation. Then semi-urban pilot is at IIT Kanpur, inside the IIT Kanpur campus. Urban pilot, again within the campus. One suburban pilot is being executed by Netra, NTPC Netra, and then urban pilot TERI is executing with the help of BRPL. Similar to 5 pilots in India, US also has 5 pilots, in which one is rural district pilot at NRECA, then semi-urban distribution pilot at Washington State University, semi-urban distribution pilot 2 at TAMU, then urban distribution pilot 1 at Spokane, West Virginia, Washington State, and then urban distribution pilot, which is now being executed in WSU. Now, when we talk about the Indian pilots, so first I'll discuss about the rural pilot, which is being executed at Harnu village, which is 45 kilometer from IIT Kanpur. And in that village, we have identified two hamlets which were earlier unelectrified. And in 2019, before 2019, when we identified those hamlets, those were not electrified. But in 2019, they got electricity as part of the Saubhagya scheme. And in Chabba Nevada hamlet, we have 70 kilowatt peak of solar, 50 kilowatt, 100 kilowatt hour of battery energy storage system. In Bargadia Purva hamlet, we have 30 kilowatt of solar, 30 kilowatt of biomass, and 50 kilowatt, 100 kilowatt hour of battery energy storage system. So in these two hamlets, we have one AC-DC AC interconnection as well, where we can share the power in any side, because now both of the hamlets are also connected with the grid. So any side of the grid fails, you can transfer the power from either side of the village hamlet. So this particular pilot is being executed by Siemens, and hopefully by end of January 2023, we'll be ready with that pilot. Then semi-urban pilot is being executed at IIT Kanpur. We have identified lane 32 and lane 33 as suburban setting, because in those two lanes we have mostly single story houses which will mimic the suburban kind of concept. So we have identified that for this suburban pilot implementation. So in these two lanes, we have identified 30 houses of faculty members where we have installed 50 kilowatt peak of solar rooftop. And then we have centralized battery energy storage system. In lane 33, we have 70 kilowatt, 140 kilowatt hour of lithium-ion battery storage system. While in lane 32, we have 50 kilowatt and 100 kilowatt hour of battery energy storage system. Two EV charging stations also we have installed, and um, we have also added 25 kilowatt peak of solar PV with that charging station. So these charging stations are ready and we are using that as of now. And the most of the installations in semi-urban pilots are completed. There were some issues related to battery management system, which Siemens is trying to address. Otherwise, we are almost ready with that pilot. Then third, urban pilot, we have identified two multi-story buildings of campus, which are basically faculty residential towers. And there we have installed 25 kilowatt peak of solar rooftop and 25 kilowatt, 50 kilowatt hour of battery energy storage in both of the towers. Plus, we have also installed around 775 ton hour of thermal energy storage system at Center of Environmental Science and Engineering building. So this helps in addressing the peak load challenges which we have during peak summer period in campus. And this thermal energy storage system is installed and running well from since 2020. Then another important component in the pilots is the ADMS development, which we are doing with the help of our partner Synergy Systems. And there we are developing multiple modules where we will integrate all our pilots with that ADMS system, so that at one location we can monitor and control those pilots. So this will be installed in the campus. We have our smart grid control center in the campus. There we will install ADMS and we'll monitor from that location the critical aspects of all three pilots which are being executed at IIT Kanpur. So this Harnu village, if you see the figure, this is the typical architecture we are using. In these two villages, we have 25 kilowatt AC DC AC converter for providing the flexibility in energy transmission between these two hamlets whenever the energy requirement occurs from any side of the hamlets. So the Siemens is implementing microgrid controller in both of the hamlets, and we have developed the operating philosophy for both of the hamlets, where we prioritize the type of sources we need to dispatch at what time. So depending upon the requirement and the priority, we have developed the particular algorithm which Siemens is implementing in the microgrid controller. So we will be able to optimize the utilization of energy sources, which are solar, battery energy storage system, as well as biomass system. In this particular village pilot, we have also given 6 solar water pumps for irrigation purpose, because their prime requirement was the solar irrigation, the irrigation water requirement. So for that, we identified 6 locations. From there, they can get the field irrigated. These solar pumps are running very well from last 2 years. Then, if you see the total population of those two hamlets, so we have seen that there are around 700 people. We have got those who have got the benefit of this particular village pilot. These are the few pictures, recent pictures we have taken with various implementations like biomass. We have control room ready with rooftop solar pumps. You can see the figure. Then control room and that ground mounted solar PV 70 kilowatt at Chabba, Nevada. And then these are the pictures from recent meetings we had with the village society. So for implementation, we are taking help of village society. So in fact, we have created one village society in which the panchayat members are the member of that society. One member is from our NGO, Samik Bharti Foundation, and two, including myself and the IWD executive engineer, Mr. Vinay Tiwari, are part of that society. So that society will be empowered to uh, bill the customers, because the DBVNL will give power at single point at each and every hamlet. And from there, the distribution will be the responsibility of the society, because they will bill the customer, and after collecting the bill, they will in turn pay the required amount to DBVNL. So in that way, the internal energy utilization will help in reducing the bill, because you have solar PV and all which will be utilized internally. So total energy import from utility side will be minimum. So in that way, the villagers will get the benefit of reduced energy bill, which we have already promised to them. Now, in lane 32, 33 of our semi-urban pilot, we have, as I mentioned, we have 30 houses with 5 kilowatt peak, 140 kilowatt hour and 100 kilowatt hour of 2 sets of battery energy storage system and 2 EV charging stations. These implementations will have connectivity with the existing SCADA system, and it will be sharing data with the ADMS system, which we are right now developing, so that using those single line diagrams and the dashboards, we can monitor the performance of converters and the total energy generation from the control center. And this is the architecture we are having for lane 32 and 33 in case of semi-urban pilot. Then for urban pilot, the right side, if you see the figure, this is the typical architecture we have developed, and the implementation is completed for the urban pilot. There we have 25 kilowatt of solar PV, each in C and D building of the campus, and then 775 ton hour of thermal energy storage system. So this is like the pictures from the thermal energy storage system, and this is the time when our director inaugurated the thermal energy storage system in 2021, and the important points related to thermal energy storage systems are that we are utilizing the glycol based solution with phase change material, where we cool the material to -4 degree. When we have solar energy sufficiently available, we utilize that to cool down. And when we have the peak load condition, we dispatch that energy in the form of air conditioning. So this year, since we saw the peak load condition during summer period, we cut off the portion of our air conditioning system from the main grid, and we supply the power, basically the air conditioning cool air, through the thermal energy storage system, and in that way, to some extent, we could address the peak load condition in the campus. And this right side bottom, if you see, this is the integration with the existing SCADA system, which is being done by these energy systems. Now, this is the picture of our Smart Grid Control Center at IIT Kanpur campus, where we will be implementing the ADMS system. So, if you see the ADMS architecture, we will be utilizing the existing SCADA system, because our campus is 100% on SCADA. We have 10 substations of 11 by 440 and 133 by 11. All are integrated to our SCADA system. So the data from all the substation is coming via RTU to our SCADA system, and the SCADA system is implemented by Synergy, which was as part of our another project, that is a Smart City pilot project funded by Ministry of Power. On top of that, we are implementing the ADMS system, which is the 100% indigenous, developed in collaboration with Synergy Systems and IIT Kanpur. There we have developed topology analyzer, state estimator, distribution power flow, or in fact, volt war control has been developed, and we have deployed in the campus, and it is under testing phase right now. Some of the applications which are in the development phase, like fault location, isolation, and service restoration, and loss minimization via feeder reconfiguration and load balancing. These are under development, and soon we will finish these development activities, and we will be ready with our full-fledged ADMS system. GIS is already been implemented, and using OpenStreetMap, Synergy Systems has integrated the ADMS with the GIS system, and we can see the single line diagram on the GIS map. Salient features of ADMS is that we have real-time communication interface between SCADA and ADMS, and the ADMS system is developed on common information model, so it is 100% flexible, and the data interoperability issue which we face in our conventional SCADA and ADMS system will be addressed with the help of this development, which we will be having soon ready in March 2023. Then we have Terry urban pilot projects, which are being implemented with the help of BRPL. So there we have 3 categories of implementation. In category A, which is being implemented in the New Friends Colony of Taimur Nagar, there we have 288 kilowatt hour of energy storage on lithium ferrous phosphate chemistry. The primary application of the category A implementation is transformer DT overload management, and the secondary application is energy arbitrage. In category B, we have 216 kilowatt hour of battery energy storage system, again on LFP technology. And the primary objective of this development is to provide the backup power to the society. And then secondary objective is the energy arbitrage. Third category has 72 kilowatt hour of energy battery energy storage system, where the primary objective is to utilize the energy time shift, and the secondary objective is the dispatchable solar PV generation. Then some of the activities which are still going on in the TERI BRPL pilot is the integration of all these three pilots uh, to the SCADA system of BRPL, and then the connection of the data from these three categories to BRPL site using some of the technologies which we are still in discussion with the vendor, is that how we will integrate, whether it should be through SSL or through some other method. Then suburban pilot project of NTPC Netra. It will have 4 megawatt of solar PV and then 1 megawatt hour of lithium and energy storage system. So the overall objective of this pilot is to establish an off-grid microgrid for NTPC Netra. Means the overall import from the utility grid will be minimum. In fact, the ultimate objective is that if they can cut off 100% from the utility grid. Then some of the important activities in terms of R&D effort, of course, these will be discussed in other sessions as well. So if you see that we have multiple themes in UISS project related to research and development, like energy storage, microgrid and active distribution system, cyber security, DSO functions, regulatory aspect, and benchmark system development. In all these themes, we have multiple R&D efforts, and we have translated those efforts in the form of our major outcomes. So if you see the major outcomes, we can categorize them into three major bullet points. One is scientific, where we can see we have published 105 journals till now, 154 conferences, then 4 patents. Out of that, 1 patent has already been granted, which was on micro phasor measurement unit. We have 12 PhD graduates, 38 ongoing, 20 master's students, 17 postdoc students are also there. Then in terms of product development, we have power amplifier of 2 kilowatt developed at IIT Kanpur, micro PMU utilizing the Navic clock, ADMS development, which is being done with the help of Synergy Systems. From US side, we have CP Scinet tool developed at Washington State University. Then cyber and physical resiliency tools at WSU, microgrid protection, reliability and transactive control framework at KAMU, retail market models developed by MIT, and solar PV forecasting web tool developed at HNEI. Then workforce development, as you know that the knowledge dissemination is our important component of this project. So we have till now trained 150 research staffs, 64 students, 90 utility professionals, and 35 ITI graduates. Then major deliverables, we can categorize them into 4 major portions. Lab test bed, I have already discussed. Field pilots, 10 field pilots are there, 5 in India, 5 in US. Then policy documents, DSO white paper is ready for launch. Other technical reports are under development as part of our overall project objective. Then different benchmark models which are developed as part of our USS project. And then key highlights, if you see from the pilots, we, especially if I talk about the rural pilot, we have uh, ensured that we provide 24/7 electricity to rural people and provide the local employment through the food processing plant. We have reduced approximately 350 tons of carbon emission per year with the help of solar PV installation. In fact, if you see the Netra pilot, the benefit will be 11 folds because their size is quite large. DSO white paper is another value addition for the country. And then ADMS platform, which is developed indigenously, and then reliable power sharing with the help of AC/DC AC converter. Then we have multiple knowledge sharing and technology discussions between US and India counterparts. And in fact, we are sharing a lot of learnings between India and US. So that's all from my side. I'll request Sanjeev to please take it forward.
Yeah, thank you, Professor Ankush. Briefly, I will cover all the updates from the US side. I mean, they are just glimpse of, oh, sorry. These are glimpse of the US side update. So we will cover the major theme-wise related, but rise of now where we stand from the US side, like you can see the projections, the percentage wise. So we'll be reaching like 10% of the, I mean, coal. I mean, I don't know, ideally we should reach the 0%, but this is the projections. So, and the 44% of the renewables by 2050. So these are the projections from EIA, Energy Information Administration. So they projected towards the 100% renewable dominance, and then 0% coal, and the like carbon neutral anyway to 2045. So how we are actually addressing some of the challenges in the road. So these, the first one we are covering on the benchmark model side, like we developed the cyber physical synthetic network models, as well as the field pilots models, as well as the other emulator models. So we cover like a real time, offline, even the quasi steady state, steady state. So all the models being developed from the USS project, actually we hosted on an open source platform, so everybody can access here and they can utilize for their own research and development or validation of any technology. So, and moving on to the next one, so the microgrid. So there are network microgrids and the micro connection interactions, if there are still challenges and the visibility. So there is a big challenge from the visibility side and how the control framework will work from the operator side. So in this one, so you see the one of the example we are shown on the right hand side here. So how does the microgrid energy management system or the network microgrids coordinate with the ADMS or the system operator at distribution system level? In this case, so we just provided ancillary services, but there are other services or other schemes. We looked at it like a reconfiguration of the network microgrids and how effectively we can restore the network in case of emergencies or extreme events, and how do we really enhance or effectively manage day-to-day operations of the distribution grid. So for that, like the network reconfiguration, control of the network microgrids, loss optimization, the protection, especially because when there is a bidirectional power flow, and if you're looking at like AC microgrids and DC microgrids or hybrid microgrids, and the bidirectional power flow is a really challenge, because as of now we have a unidirectional protection schemes exist in the field, and how does that will enhance, or maybe how do you really modify in order to make it more cost effective? And those schemes actually we address from different partners and collaboration from US and India. And the resiliency, because resiliency is another important aspect of the distribution grid, because we have seen major outages from the distribution side, not on the transmission, even though we have some events, but it's no majorly focused or centric around the distribution system. So how does this project bring up new tools or the resiliency analysis frameworks? So it's WSU and WSU, WVU, and most of the US and India partners collaborate on these tools. I mean, the WSU, WVU majorly contributed towards the development of the tools, like resiliency planning and investment analysis. Okay, what if I add more storage distributedly? So will that enhance my restoration? And then will it really increases the restoration time? I mean, can I do it like within a 4 hours or 24 hours? Right now, it takes like sometimes hours, sometimes weeks, sometimes even months. So it depends on what is the severity of the extreme event. And then what if the cyber security? Okay, in case of the distribution system, because we are increasing the surface area, because you are enhancing the ICT technologies, that means you are actually adding more smartness to it. But meanwhile, you're also increasing the area to be affected or maybe can be intruded from external bodies or so that we have the cyber security aspects and then cyber physical security as well. So there is a metric to evaluate or assess the system security level. So, and we use the completely open source platform. So these are what are the tools and frameworks we developed is actually open source. And like you see the HTML and even the databases we use, the MongoDB and Postgres, those are open source. So we utilize them to make it more convenient for the utilities to adapt them in the field side if there is a provision to do it. So right now they are looking at like our US utilities and other partners are actually looking at how do they adapt it, or at least like make it for and take it forward to actually see the real impact analysis. And so then the other aspect like is the data driven. So right now we have gathering a lot of data from different sensing technologies. So how do we really utilize these data from coming from different sensors or different measurements? And do we really predict or estimate or forecast the invisible or maybe unobservable units from the operator perspective? Because that's a major challenge from the utility side. So when you look at the utility operator, they do not have a direct visibility from each DER owned and operated by third parties or even by the residential customer because of privacy, because of other issues. So how do we really estimate from the known ones, the unknown ones are? So that is one aspect we looked at it, and even we looked at it, the forecasting, like we need to have a clear understanding of what the load is and what the load pattern should be and what is the generation look like for the next hour or for the next day. So for those actually we developed all these data driven tools like a forecasting side, behind the meter estimation side. So even we further looked at the EV side as well, but we just covered these one. And now the reliability, the other aspect is the reliability aspect. So here, so right now we have the SciFi, SciD and the existing metrics. So how do we really come up with the new framework that include the distributed energy resources? Because we didn't really look at it, how the reliability indices look like if you consider the residential side, commercial side, or the industrial scale of the distributed energy resources. So these are the another framework proposed by the Tamus and the Professor Chenna Singh. He's here so to give you more insights in it if you need. And then the algorithm wise, okay, operation side, what we actually looked at it like. This is one of the example like World War control, but we also have the control other frameworks. So the World War, we have a different centralized, decentralized, and even the distributed. So and the local. So there are different algorithms developed by the different partners, and they consider differently because if you look at the radial distribution system, the mesh network, so one is applicable to radial and other is applicable to the mesh. So how do we really make it a common notion or maybe the common technique for the both the grid? So one of the technique they use the current injection model to make it a PAC algorithms, a coaxial atomic coordination algorithm to be adaptable for both the types of distribution systems. Likewise, we have the decentralized local. So I'll discuss in the field side as well. So then moving on, the DSO, the another one is the retail market, right? As of now, we have the wholesale market. So how do we really look at it, the retail markets or the P2P trading, so transactive energy. So those things already been covered as a part of this project. So I'm not going into the technical aspect of it because of the interest of time. So, but we'll be happy to discuss offline. Then coming to the validation side, like validation is really a key to key to the deployment side, because before you go into deploy in the field, first we need to understand what the what if cases or if else cases are, and what if this goes wrong. So those things are actually done in the lab scale. So fortunately, we have enough representation from the national labs as well as the universities and industry. So Bunsen Mech actually have the NIA Network Integration Automation Lab, and where we can we are testing the communication things, even advanced LTE bands also is there to test it. And Enreal is the one of the key partner in the validation side because they have the physical wind as well as the battery energy storage systems and the solar PV. So we integrated, even tested the technologies in their laboratories. And likewise, we have TAMU and WSU Hawaii and WVU. So WV have the cyber physical. So every test bed is unique in their aspects, and we are testing different technology altogether. We are not actually sharing the same thing, but we are actually sharing the common benchmarks to validate the same technology to make it more understandable. So, and the field ones, actually we have the rural, urban, semi-urban, and then the urban 2 and the semi-urban 2 case study, I mean the pilots. So rural one, we have a different notion altogether for compared to the India side, because the rural is slightly different in US. So we took the cooperative, the Opelco, Orcas Power and Light Cooperative. So this is a really small in scale. So we consider this as a rural pilot. So what we did is actually they are facing a single outages because they are fed from the BPA transmission. So they wanted to consider the resiliency enhancement from the battery energy storage system. So what if they install the enough battery energy storage system as well as the offshore wind in their islands, because the Opelco serves the 3 islands. So we consider the San Juan Island for a case study, and then so we took the actual data from the field and we analyze all the data sets for the different season, because we have 4 seasons and each season have a different issue. So there's no commonality exists between all the seasons, but the biggest problem is the winter. So in winter, so they're running out of the energy supply from the grid if there is a single point failure, because there is only one feeder service actually supply the San Juan Island at the complete Opelco a service area. So what we did is like we analyzed the complete seasonal load profile, as well as we took it, okay, what is the optimal size we can propose just to serve the critical loads, because that's the major goal for them. We are not actually looking at a complete load, even though that is priority for all the utilities, but that's not technically or economically feasible. So we are looking at only the critical loads, and the percentage wise is like somewhere around like 15 to 20% overall. And then there are like a high priority, medium and low priority loads. So we only consider the high priority load, and we even consider the what is the set points for the DERs, which are exist in their own sites or the service areas. DERs like DG backups, and as well as the distributed solar, even though there is completely a distributed in nature, but we consider as a centralized to just make it more simple for the analysis purpose, or make it clear for them. And this is the actual results. If you look at it, like what if you consider the PV plus battery, because they have the high penetration of PV, and the battery energy storage system and the wind are like the future deployment. So what is the enhancement look like for serving the critical loads in case of there is an outage? So what is the key? I mean, whether we can able to improve or whether we can able to serve all the critical loads. The point 2 is, yeah. The point 2 is actually it replicates only the percentage wise the load in the serving. It doesn't indicate the complete resiliency in terms of the system level. So it is only the what the percentage we are serving for the critical. So we are covering almost all the loads for the complete 24 hours. So now moving on to the semi-urban. So this is a campus level semi-urban pilot at Washington State University. So what we are doing is we have a critical facility, that's a WSU facility, which serves the 24/7 operations. So we are backing up that building through a battery energy storage system. So we are deploying it, and so that it will ride through the at least 2 hours outage. That is typical in the Washington State campus. That, I mean, even though we have a backup generation, but we just want to make sure like we have a immediate supply to the critical building, because that is more important for like scheduling or even like dispatching the crew for restoring anything. So here this is actually the schematic of that, how we are deploying that energy storage system for supplying the critical loads in case of the outage. And now moving on to the semi-urban pilot 2, that is from the Texas A&M University. So here they are looking at the nanogrid market participation. Like, okay, what if we consider the residentials nanogrids, and if we make them as a clusters or the aggregators, so what is the risk involved, and how do they actually coordinate and exchange the power through a transitive mode? So that is the aspect we are looking in the pilot of the TAMU case. So So there are some risk maps and everything actually probabilistic. So I'm just quickly jumping through all the pilots. Then the so urban pilot from Avista. This is a utility, and Avista serves the Eastern Washington area, service area, and then they have the battery energy storage system as well as the solar PV units. So the solar PV units of 100 kilowatt, and then now what we are looking at it is, so this is their typical site. Then how do we really leverage these resources in terms of providing a services to the utility? So here we looked at one of the volt war optimization. So what if, can we really provide a volt war services from the battery energy storage system and the solar PV? Initially, we thought of considering the battery energy storage system, but now we are only focused on the PV because the PV is more majorly penetrated through the networks, but the battery energy storage systems are still limited in number. So we are considering the PV units, and then we are applying the different techniques. Before we go for all the techniques, we are transforming what we developed part of R&D. Now we are taking into the field side. So we have three different techniques like a decentralized, centralized, and distributed. So each from different university, one from the WSU, another from the WVU, West Virginia University, and another from the MIT. That's a distributed pack algorithm. So three different techniques we analyze in the offline case study. Okay, what are the scenarios actually they are facing? It's an over voltage issue or under voltage issue or voltage support issue. So in those cases, how do we really minimize the losses? So we looked at different case scenarios before we go for the lab testing and even further for the field deployment side. So we analyzed and then we concluded, okay, local will be the best way to integrate and deploy it in the field. And then now we are working on the lab scale. So this is look like this is the lab test bed we have in the Avista Energy System Energy Innovation Center. So in there we are actually embedding everything in the microcontroller. So we already did it. Now we are testing in a different case scenarios in similar to the field side. And once it is validated in this environment, now we are moving on to just take the same microcontroller, that is nothing but the RTAC here. So and then we are going to deploy in the field, and then we'll coordinate with the PV units in the field. So and then we'll share the complete results in the end report. And yeah, this is the plan. And then moving on to the last pilot of the project from the US side is the GE-ADMS. So what we are looking at here it is how exactly we can coordinate the campus, the WSC campus microgrid, because it isolates when there is an outage from the upstream from the Avista service feeder. So here we are considering the GE-ADMS. We already have the enough enough modeling and then the coordination with respect to the data point side, but this is again a still emulated situation. This is not completely executable, but we are having the data feeds from one way, and then we are taking that data feeds from the PV and the battery, and then we are exercising different case scenarios from the ADMS side and the coordination from the GE MEM side. So that is the last pilot, and then I'll hand over to Professor Anurag. Thank you.
Okay, well, thanks, Sanjeev. So I'm going to just wrap up the progress from the US side and also highlight some of the collaborative activities that's going on between US and India. So in terms of key activities that you see here, one was trajectory control for nanogrid, which is with TAMO, CP SciNet tool, which is cyber physical synthetic network generation based on the user demand. And then this federated test bed with NREL and WSU in progress. And then also retail market. And then this resiliency tool, RPI tool, and also cyber physical resiliency and the PV forecasting tool. So if we think about collaboration between US and India, there is a lot to capture here. These are just some examples. So in each team, we do have some collaboration going on. Like in team 2, we do have a IT Kanpur and I know ITM and IT Roorkee working with WSU, which is on benchmark feeder model development of different kind. We do have ITK and ITR and WSU working on real-time feeder model development, and then also a federated co-simulation. Right now we do have with the NREL, and then we'll be extending it with ITK. Then theme 4, we work with IT Roorkee for microgrid management system with storage and DERs. We also has some collaboration between IT Bhubaneswar and TAMO for microgrid protection. And then WSU and ITK working for distributed control of microgrid with different voltage control techniques. For theme 6, we had WSU and ITR collaborating for volt war control, again with the microgrid and within the microgrid and outside microgrid. Then we had collaboration between Hawaii and WSU and ETAP and also IIT Kanpur working for solar and load forecasting and behind the meter estimation. We had WSU ITK on federated co-simulation testbed, and then with MIT and IT Delhi on interaction for system operation, for especially for non-market also, and market, which is part of theme 7. Then with IT Roorkee, we had demand side management and optimal operation of DR plant. So some are in kind of completed, some are still in progress. Theme 8, we had testbed activities with, again, ITK, WSU, Envo for federated testbed with TAMU and ITK for control and validation of nanogrid. And then with IT Roorkee, WSU, real-time NHIL simulation. Then theme 3, we had Hawaii and IT Bhubaneswar working with ITK for battery modeling. Then we had ETAP and Hawaii and WSU working with ITK for impact study of V2G studies. And then TAMU and TERI for transformer life assessment with battery. And then LBNL and TERI working for maximizing the value of BSS. Theme 5, which is cybersecurity, we had some collaboration between WSU, WU, ITD for smart grid security, and with working with IT Kanpur, we had post-simulation testbed, including the cyber. And then also with IT Roorkee, we had one intern recently, which was also looking at cyber resilient microgrid control and planning for that. Theme 7, IT Delhi and MIT collaborating together for distribution market design. Also ITK involved and WSU. And then we had TSO, DSO coordination, work going on with MIT and ITD with WSU, and then also retail market models with ITD, MIT, WSU, and WE. In theme 9, we had WSU and ITK working for knowledge sharing of semi-urban rural field pilots, and then working between WSU, PNO, and TERI for knowledge sharing of urban field pilots and demonstration, and then just sharing the knowledge from different field demonstration between WSU and ITK. The last one, theme 10, is WSU and TERI working with ITK for comparison of India and US policy standard. That Dr. Bose has been leading for this. And then WSU, TERI, and ITK, MIT, and ITD working for review of policy regulations. And then finally, impact analysis with WSU and TERI. So again, these are some examples. There's a lot to talk about each of these. So far, in terms of project outcome, we would also like to highlight that there has been at least 10 joint paper published with the US and India co-authors. Then we already saw that there was 81 journal paper from India side and around 20 from US side. In terms of conference proceedings, there are at least 15 published where US and India are co-authors together. And then around 134 in India and 37 in US. In terms of patent and copyright, there are several that Ankush talked about earlier, including converter design, and there's a DFIZ wind system supported by the DC microgrid. And then multifunctional three-phase, single-phase solar PV based transition capability, and then micro PMU and everything that Ankush talked about. Tool development, again, CP SciNet is I work with the WSU. Then CPSAM and RPIA is a resiliency tool, one focused on cyber, one focused on weather impact. And all this microgrid protection, reliability, and transactive control. So I'll not go into all detail because we already have talked about, and then of course we have some test bed and students graduated, and then training of human powered. So just to conclude, of course, distribution grid is going through a major transformation, and EYSS is a major step towards that to provide solution with a big impact in terms of demonstration, in terms of collaborative papers, in terms of technology exchange, in terms of training, in terms of coming up and emphasizing the issues with some metrics, and even looking forward for resiliency, which is future thing to get it done. Of course, several of the challenges will have some similarities, some differences between US and India, and we are working on a different report which will highlight that. And then if you look at 2017 and now, we do have several things to report that what came out of this, working individually and working in collaborative manner. And I'm sure that by the time this next year we finish, we'll have more to report. Okay, well, at this time I'll stop, and of course we acknowledge our funding agency to do this work.
Thank you, Anurag. This was the only session of giving some kind of glimpse of the project. And then we have panels on different, very important thematic area and by very eminent experts. So if you have any quick questions about the project, maybe not from review point of view, but maybe getting some information. I know the reviewers are there, but anything, anyone? Yeah, so you will get chance to visit one of the site today afternoon, and you are also most welcome to come to Kanpur. The sites are ready. Final commissioning is not done, but they are working actually. They are producing energy and we are utilizing that. So most welcome, our alumni also, some of them. Yeah. This time we have not planned because very time schedule is very tight, but we can plan. Yeah, we can plan. Definitely, that's a good idea. We were thinking, but now we are not very sure about weather also because a lot of fog is there. So if we show, you will say that nothing is there. So that really doesn't give good impression. Yeah. So yeah, if you don't have any questions, thank you very much for joining this session. And we have a tea break for 15 minutes and then we'll reassemble for the next session. Thank you.